Okay, kids. So I want to try to kind of have to wing this through a couple of different ideas. So here are the big equations relating to capacitors. So the first one is, these are all on your equation sheet. So this is showing you the energy stored in the capacitor, and there's two different ways you can calculate this. One is the charge that's carried on the capacitor times the voltage, and the other one is the value of the capacitor times your voltage squared. So without going through all of this, basically, like, here's the simple one. So this is Q, right? So that's your charge. And then measured in coulombs. And then you got delta V, which is joules per coulomb. The coulombs cancel out, boom, you get joules. Hey, we're off to the races. If you have capacitors that are hooked up in parallel, okay, and I'll show you that in just a second, then that's just the sum of them. If you have capacitors that are in series, then that's just like resistors. You just add the inverses of them, and then you take the inverse of all of that. Boom, there's that capacitor. Now, to actually calculate the value of your capacitor, and that's epsilon naught A over D. So with all of that said, so what I've got here is a couple of things. So I've got a voltmeter hooked up that right now I've got hooked up across this capacitor right here. And so this is where this gets messy. So I've got a power source here, a simple 9-volt battery. I've got a couple of switches and a conglomeration of wires. So let me kind of take you and trace through this. So this is the icky part of everything. So right now, here is my voltmeter. So I'm going to disconnect that for now, just so that's out of the way. Okay. And there we go. Okay. So I'm just going to take this out of the way. I'll put it back in just a second. So I've got my battery. It's going to an LED light, and then I've got this second LED light hooked up in parallel around a capacitor, and then I've got a second switch here that connects this whole thing. So what I'm going to do right now is I'm going to discharge the capacitor. Okay, so here's what I'm going to do. So I'm going to, for now, just to kind of show you how it works, we'll get to the voltmeter in just a second. So for now, I'm going to throw this switch, and I've got this parallel circuit that's connected to the capacitor. That switch is open, so there is nothing happening over here. So what's going to happen is I'm going to throw this, okay, and notice that this LED light comes on very quickly. It went bright, and then it's going to stop. So what's happening is that at this point, this thing has shut down. So this is going to be the difference when you get into the charged for a long time or it's charged for a short amount of time. So when this thing is first thrown, the LED light comes on, it goes very bright, and then it's going to fade out as that capacitor builds up charge. Once that capacitor builds up charge, then it shuts down the circuit. So now I'm going to throw this switch, and that's going to shut down everything in the main circuit, okay? So at this point, this capacitor is holding charge. So what I'm going to do next is that I'm going to throw this switch, which is going to allow the energy stored in the capacitor to flow through the blue LED light. So I'm going to throw that, boom, came on very quickly, it got bright, the energy was discharged from the capacitor. Now, when I throw, now I'm going to open this back up, okay? So now, when I throw this switch again to allow the electricity to flow through the main part of it, then that LED light's going to come on, it's going to get charged, boom, there you go. Now, I'm going to discharge everything again, okay? So that just turned on my little LED, my blue LED light. A little bit. Okay. Now, here's going to be the next thing. I want to hook up my voltmeter across the capacitor. and I hope I guessed right in terms of what's positive and negative. Oh, I did. Okay. All right. So here's what we've got. So I'm going to discharge that capacitor. And you'll notice that the voltmeter is dropping to 0. So what I'm going to do, this is what I want you to watch. I'm going to close this main switch. Okay, I'm going to close the main switch. And then what's going to happen is that you're going to see the voltage build across that capacitor. So I'm going to drop this down, okay? And you'll notice that that voltage rose. So what that's showing is that that capacitor is holding that charge. So this is measuring the voltage across that capacitor, which is also the same as the voltage that is stored in the battery itself. So those two values are the same. So now what I'm going to do is that I'm going to open up this switch on the main circuit, and then I'm going to close this switch, and what's going to happen is that that battery is going to discharge and that light's going to come on. So I'm going to open up this, drop this one, the bulb flashed, now that voltage dropped. So what's happened is that I took that energy that was stored in the capacitor. I could calculate that energy that was stored because I could use this handy equation. So if I knew like how much charge was on the capacitor, or I knew the value of the capacitor itself, and this is a, hold on, it should say on here somewhere. Oh yeah, so this is a 100 microfarad capacitor. So I could change, this is 1,000 microfarad capacitor, change that into farads, then multiply that by that voltage, which was about 6 volts. I could find out how much energy was stored on that capacitor. So there you go, kids. Now, in terms of like being hooked up in series or parallel, it's the same idea. So if I wanted to hook up a capacitor in parallel, okay, instead of like a light bulb, I would just grab another capacitor. I would hook it up like this, like so, okay? Now I've got two capacitors that are hooked up in parallel, and the same idea is going to happen, okay? So now what's happening is that you'll notice that this LED light has gone out again. So now I've got these two that are hooked up in parallel. So in this case, because of the fact that they're hooked up in parallel, I would take 1,000 microfarads plus another 1,000. So this would be an equivalent of a 2,000 microfarad capacitor because these are hooked up in parallel. Now, if I hook them up in series, okay, then I would add the inverses of them. I would take 1 over 1,000 plus 1 over 1,000, and that would decrease the value of my capacitor. Just like resistors that are hooked up in parallel have a decreased value for that resistor. Hooked up in series, it gets bigger. So they're like opposites of each other. Okay, so anyway, so that's what you needed to see, and we're good. So, all right, hopefully that helped. See you, kids.